what do we call it? We're going to write a little description off to the side, and then basically like how do I want to say it? A practice reaction of what it could look like. So synthesis or combination is two things become, and if I was better with words, I would have said two reactants or more, two or more reactants become one product. That is what a synthesis is. So A plus B becomes AB. Now, the cool thing is if you have this type of thing, you can sit here and go up here and look and say, okay, where are all of those? Basically, I'm looking for one product. Here I have 1 plus 1, that's 2 products. Here I have 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 1 product. So right there, that tells me that that's a synthesis. A decomposition is one reactant. I'm going to use good terms, the best terms. I'm going to use better terms, I hope. One reactant becomes multiple products. Ooh. So we'll just do the opposite. The decomposition is the opposite of the synthesis. AB becomes A plus B. So here we have one reactant, multiple products. Boom. Are all these just going to be in order? We'll see. Single replacement, or what is commonly now referred to as displacement. An element, that's a key. It has to be an element, replaces another element in a compound. So A plus BC could yield B plus AC, or C plus BA. Depending on what type of element this is, if this is a metal, it's going to replace the B like that. I'm going to go ahead and put metal there, or something that forms a cation, or non-metal, or something that forms an anion, it's going to replace the C. So do we have any elements? Oh, wow. I can't read. It's all the spacing here. You guys should have called me out on that. I read this as just one reactant here. There's multiple reactants. There's 2. So again, I'm making mistakes. Spacing here messed me up a little bit. It's quite a bit of space. Apologize for that. But here we have one reactant yielding multiple products. So that's going to be the B. If we take a look here, we have an element in a compound. And then over here, an element has been displaced. And aluminum has replaced that element in this compound. So that would be a single displacement reaction. Double displacement reaction. 2 cations switch places. Two cations switch places. So AB plus CD yields AD plus CB. Notice that the cation, which is written first, is still written first on the product side. Cation, which is written first, is still written first on the product side. And basically, they almost did the same order. Here we have lead, and lead has switched places with hydrogen. Lead was with the acetate, now lead is with the sulfide, and hydrogen was with the sulfide, but now it was with the acetate. So that is a double displacement. Last one, CX plus HY, some type of hydrocarbon, reacts with oxygen to form carbon dioxide and water. Those are always the products. Carbon dioxide and water are always the products for this combustion reaction. So this is a combustion. So those are the 5 reaction types that we have. And these are examples of those. Now let's go ahead and balance these. To balance these, we need to make sure that the number of atoms on this side is equal to the number of atoms on this side. Excuse me. So if we take a look, this subscript tells us that there are 8 sulfurs here. There is no subscript here, so that tells us that we have 1 sulfur. So we need to multiply that 1 sulfur by 8. Well, that screws up our chlorides. Here we have 2, and here we have 8 times 4, which is 32. So now we need 32 chlorides on this side. And how do we make 32? We multiply 2 by 16. Yep. Here we have aluminum. Here we have 2 aluminums. So let's go ahead and start by putting a 2 here. Here we have 2 coppers, so we'll go ahead and put a 2 there. Sometimes everything doesn't work out nicely because we always save oxygen for last because it's in most compounds. But here I see I have 3 oxygens, so that means I'm going to have to put a 3 here. I've already determined I have 2 coppers on this side, but something just changed all that. Now I have 6 coppers over here, so that means I'm going to have to go back over here and change that to a 6. So 2 aluminums on each side, 6 coppers, 3 oxygens, 3 oxygens. Let's take a look here. 1 magnesium, 1 magnesium. I'm okay with that. 2 chlorines. This 2 refers to these parentheses, so that means 2 times 1 chlorine is 2. 2 times 3 oxygens is 6. So I'm going to have to put a 3 in front of that oxygen. Down here, if this thing in parentheses is on the other side as well, we can keep this as a whole thing. So we have 2 acetates, that's C2H3O2. So I can put a 2 here. That 2H right here is canceled by these 2 H's right here. 1 PB, 1 PB, 1 S, 1 S. Here we have 7 carbons. So if I put a 7 there, 14 hydrogens. So I need a 7 there because 7 times 2 is 14. That gives me 7 oxygens plus 14 oxygens. That's a total of 21 oxygens on this side. What can I multiply by 2 to get 21? Anyone? What's 21 divided by 2? Nobody knows. Well, let's ask Alexa, or whatever her name is. 21 divided by 2?
That would be 10.5.
10.5. So if we take a look, 10.5 there, we cannot have 10.5 there because even if we look at this as moles, 1 mole, 10.5 moles, 7 moles, 7 moles, sure you can have half a mole. But if we look at this as particles, 1 C7H14, you can't have 10.5 oxygens. So we have to multiply every single one of these by 2. So that's 2. That becomes 21. This becomes 14. And this becomes 14. Easy enough. For this section right here, we do need our periodic table of elements because we need to add up the molar mass. So these are what we call the atomic masses. If I have 1 mole of calcium, that's 40.08 grams of calcium. So here I have 1 iron and 3 chlorines. So for iron, we take 1 times 55.85. For chlorine, we take 3 times 35.45. Three times 35.45.
The answer is 106.35.
Now we add these two together. 55.85 plus 106.35.
It's 162.2.
So there is the molar mass for iron 3 chloride. So once you do that, you can actually just put all of this in your calculator at once. 40.08 for calcium times 3. This 2 refers to 2 of these phosphates, 30.97 times 2, and 8 times 16. 8 times 16 plus 2 times 30.97 plus 3 times 40.08.
That would be 310.18.
Easy enough. Here we have 5 carbons and 12 hydrogens. 12 times 1.01 plus 5 times 12.
It's 72.12.
Here we have just 8 sulfurs. 8 times 32.06.
It's 256.48.
Here we have 1 strontium, 2 nitrogens, and 6 oxygens. 6 times 16 plus 2 times 14.01 plus 87.62.
It's 211.64.
Here we have 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. 3 times 16 plus 12.01 plus 8 times 1.01 plus 14.01 plus 14.01.
It's 96.11.
Almost forgot that second nitrogen there. 96.11. That's the grams equals to 1 mole of each of these substances. Calculate the percent by mass of each element in strontium nitrate. Here is the mass of strontium nitrate total. When we do percent by mass, we take the part divided by the total. So for strontium, I'm going to take the part of strontium, 87.62. There's only one of them. And I'm going to divide it by the total, 211.64. For the nitrogen, there are 2. So I need to take 2 times 14.01, which is 28.02. And I need to divide that by the total. For the oxygen, there are 6 times 6 times 16.
The answer is 96.
96 divided by that total. Now each of these are going to be times 100 because we want to make a percent. 96 divided by 211.64 times 100.
It's about 45.36.
So that's 45.36% oxygen. 28.02 divided by 211.64.
It's about 0.1323.
Need to times that by 100. 87.62 divided by 211.64 times 100.
It's about 41.4004.
And the cool thing is all these added up should equal 100. Let's check. 41.4 plus 13.24 plus 45.36.
That would be 100.
So there we go. Determine the percent mass of oxygen in ammonium carbonate. Well, we have the ammonium carbonate right here. It's 96.11. So that's our total. We have 3 times 16. 3 times 16.
The answer is 48.
So we have 48 divided by 96.11 times 100. 48 divided by 96.11 times 100.
The answer is about 49.9427.
So it's 49.94% oxygen. Now here's where we varied from our other class in the past. We decided to take away these empirical formulas. I'm going to go ahead and show you today how to do it. It's not that difficult. And basically, if you understand math and ratios a little bit, it shouldn't be that difficult to see. But we do need to know, circle all of the following that could be a molecular formula with a empirical formula of NO2. So NO2, if we take a look, we have some comments. Remember, I don't look at the chat. Oh, 10.5, there we go. Thanks, guys. Sorry I missed that. I was sitting like, nobody's saying anything. If we take a look at this NO2, basically N2O4, N3O6, N4O8, these would all be molecular formulas that fit into this. Basically, we have to look here. Can 2 and 4 reduce down to 1 and 2? Yes, so that will work. Can 2 and 5 reduce down to 1 and 2? No. Can 3 and 5? No. Can 3 and 6? Both of these are divisible by 3. So 3 divided by 3 is 1, and 6 divided by 3 is 2. So that's N3O6. Empirical formula is the most reduced ratio. So if we have this, what is the empirical formula of a compound that contains this and this? Well, we know that this adds up to 100. That means if we had 100 grams of this carbon-hydrogen compound, 86.4 grams would be carbon and 14.4 grams would be hydrogen. If we want to find an empirical formula, basically we have to find a ratio. This ratio right here is 1 nitrogen to 2 oxygens. And we know that if we take and multiply this by 6.02 times 10 to the 23rd, this is 1 mole of nitrogen to 2 moles of oxygen. So it's a molar ratio. So all I've got to do is use the techniques I've learned in the past, change each of these to moles. Every 12.01 from the periodic table grams is 1 mole of carbon. Every 1.01 grams is 1 mole of hydrogen. 86.4 divided by 12.01.
The answer is about 7.194.
14.04, not 14.04. 14.4 divided by 1.01.
That would be about 14.2574.
So if we want to make a ratio 1 to something, we need to take each of these number of moles, the moles of carbon and the moles of hydrogen. And if you want to make a ratio, like for example, for every 2 apples you get, I get 4 apples. Well, 2 to 4 would be the same as for every 1 apple you get, I get 2. 1 to 2. Basically, we reduce it. So for every 7.194 moles of carbon, there are 14.257 moles of hydrogen. It would be easier if we took each of these and divided it by the smallest number. 14.257 divided by 7.194.
That would be about 1.9817.
So to make that a whole number, 1.98, to make that 2, and this divided by its own self would be 1. So the empirical formula for this would be 1 carbon for every 2 hydrogens. Easy enough. It also reinforces using the mole concept. You could also do that with this one. This time you have 3 of them, so you would take and make all 3 and then divide by the smallest one. The problem with this one is I think you're going to find something's going to be 1 to like 1.5. But you can't round 1.5 to a whole number. So instead of 1 to 1.5, if for every 1 cookie you got, I got 1.5 cookies. Well, nobody likes breaking cookies in half, right? So what we would do is instead of saying 1 to 1.5, we would say, well, for every 2 cookies you get, I get 3. So if you had one of these, if this was 1 into 1.5 or something like that, you would multiply both of these by 2 to make them whole numbers. Excellent. Tomorrow we'll start mole and mass conversion and stoichiometry. That brings in Avogadro's number, molar mass, all the good stuff. Anybody have any questions before I let you go a little bit early today? I mean, this is review week. A lot of times in college, if you go to college or whatnot, this will be called, does anybody know? Does anybody have a brother or sister in college right now? You can type it in. I'm looking at the chat now. Does anybody know what they call this week in college? Nobody. This is commonly called Dead Week because basically the partying and everything and the craziness stops as people basically come together and try to study for their finals. So this would be considered Dead Week, the week before finals. It's a pretty crazy time because, you know, everybody's kind of cooped up and spending hours upon hours of studying. And then there's almost a breaking point for some people. I just remember one dead week, I think it was my sophomore year. And my buddy Ryan Coleman, he's like, hey, I just got back from Target. And he bought all of these, like back then the super soakers weren't what they are today, but he bought all these super soakers and basically we filled them up and we went around the dormitory squirting studiers. Crazy, but yeah, it was something that he needed. Ryan was kind of one of those kids that could only handle, I mean, today you would call it ADD or whatnot. But yeah, Ryan Coleman. That's all I've got for you guys today. Have a great day. Hopefully your studying sessions are going well. Hopefully the health of you and your family as well is good as well. If you have any questions, by all means, please stay after. If you need to talk to me about something that you've made up that still has not made it into the grade book, please stay after. I can only help you if I know what the issues are. So have a great day and take care of yourselves and take care of others.